Okay, in this video we're going to continue on with the problem that we solved in the previous video. This circuit here, we set up node voltage equations and we solved for the unknown voltages VA and VB, and here are our answers. Okay, the voltage at node A is 1 2/3 volts. So that means that there's 1 2/3 volts at this node with respect to ground. So you see between these two nodes is 1 2/3 volts. Likewise, between node B and ground is 2 volts. Okay, because remembering again, voltage at a node is with respect to ground. So, equally important as solving simultaneous equations is once you have the answers for those previously unknown node voltages, taking those quantities that are now known that you solve for, and then applying them to the circuit to find out anything you want to know as far as voltage, current, or power for the elements that are in that circuit. So let's go ahead and find these various quantities here that I have listed. So for example, now that we know these node voltages, if I want the voltage across the 1 milliamp current source, well look, this current source is connected to node A and ground. So the voltage across it is just VA. So you see the voltage across that 1 milliamp current source is just going to be 1 2/3 volts. Likewise, same thing with the 1K ohm resistor. This 1K ohm resistor, one side's connected to node A, the other side's connected to ground. So its voltage is also going to be 1 2/3 volts VA. And then remembering what we discussed previously about when elements share the same two nodes, see this current source and 1K ohm resistor, they share the same two nodes. So that's a parallel connection. This 1 milliamp current source and this 1K ohm resistor, they're in parallel. And as we learned, elements in parallel have the same voltage. So, just because we're learning this new method doesn't mean all the fundamentals that we learned previously are any different. They still exist. So in any circuit, KCL, KVL, voltage being the same in parallel, current the same in series, all those things are still true. Okay, so now the voltage across the 500 ohm. Well, the 500 ohm, it's connected between nodes A and B. So the voltage across an element, like this 500 ohm, it's just going to be the difference of those two voltages at each end. So you see the voltage across that 500 ohm is going to be 1/3 of a volt. It's just going to be the difference between 2 volts and 1 2/3 volts. Now, something that is important here is that when we set up this problem back when we were setting up the equations to solve for VA and VB, we arbitrarily define this current I2 as going left to right, and based on that current direction, the higher end voltage would be over here on node A, the left side of the 500 ohm. But you see, after we did our analysis and solved our equations, we found that VB is 2 volts and VA is 1 2/3 volts. So you see, our arbitrary direction for I2 turned out not to be the actual direction. See, VB is at a higher voltage than VA. So you see the actual polarity of that 1/3 of a volt is like this, which means that I2 is really going right to left. So you see, when you set up your equations, it is truly arbitrary how you define the currents. They're not necessarily the actual directions of the currents. You can see here I1, that is the actual direction, the one that we picked arbitrarily, right? Because VA, 1 2/3 volts, is higher than ground at 0. And likewise, these current directions through these resistors are the correct direction because VB is at 2 volts, right? So again, current flows through a resistor from the higher end voltage to the lower end voltage. Okay, the voltage across the 2 milliamp current source over here, well, that's just going to be equal to VB. That's going to be 2 volts. Okay, and likewise, the voltage across the 2.2K and the voltage across the 4.7K is also 2 volts. VB because these three elements are all connected in parallel. They share the same two nodes. Now we can also get the current for the resistors, right? Because if I know voltage, I also know current by Ohm's law, provided I know the resistance like we do in these in this problem. So I1 would just be VA divided by 1K. So VA divided by 1K. That's an A. Okay, so VA divided by 1K, that's just going to be 1 2/3 milliamps. Right? The current through the 500 ohm will just be 1/3 of a volt divided by 500, which is, well, let's write it out here, be 1/3 of a volt divided by 500. 500 is half a K, so that would be 2/3 of a milliamp. Okay, and we can check to see if these answers make sense because at any node, KCL needs to be satisfied. So if we come up here to node A, there's 1 milliamp flowing in here from the current source, and there's 2/3 of a milliamp flowing in through the 500 ohm resistor. Well, flowing out through the 1K is 1 2/3 milliamp. So you see that KCL is satisfied here, that 1 milliamp plus 2/3 of a milliamp flowing in equals 1 2/3 milliamps flowing out. And then, you know, if you want to find power, say power for the 2 milliamp current source, well, power is always just V times I for that element. So we would have 2 volts, because there's 2 volts across that 2 milliamp current source, because it's equal to VB like we talked about just a moment ago. And then the current for the current source, the 2 milliamp current source is 2 milliamps. So its power would be 4 milliwatts. And then also, you should be able to tell whether this current source is supplying or absorbing, right? Because you just look at the direction of the current on the higher voltage end, and the higher voltage end is node B because 2 volts is higher than ground. So you see this current source is supplying power, as well as this one over here, right? Both current sources are supplying power. So, you know, another check you could do on your own is find the power absorbed by all the resistors here and make sure that they add up to the power being supplied by the current sources. So the main point of this part of the lecture is just that, you know, the work doesn't stop once you have the solution to your node voltage equation. You know, once you solve for the previously unknown node voltages, right? Once you have these answers, you can then go back and find voltage, current, power for all the elements. And see, this is where you're utilizing concepts that we talked about earlier in the class. You know, KVL, KCL, Ohm's law, you know, when power is being absorbed, when power is being supplied, all those types of things. So you can't forget what we previously discussed before this method. I think there's a tendency sometimes for students that when they do a problem like this, you know, they get, you know, they're able to set up the equations, you know, get the node voltage equation, solve for the unknowns, you know, solving for simultaneous equations, but then it's as though they think, well, that's it, and, you know, this is totally unrelated to what we learned earlier, but it's not. It's all interconnected. And we're going to do more problems because you're going to see that we haven't seen a problem like this using this method that has a voltage source. So the next lecture will still have current sources, but one current source will be a dependent source. But then we'll get the problems that have voltage sources, and we'll see how we deal with those. So we're going to be on this method of node voltage method for the next few videos.